Hello, here's section 4.1's lecture. So chapter 4 is all about applications of derivatives, which we did a little bit in chapter 2, where we would like interpret what the derivative means in these different situations. And the problem was in chapter 2, we didn't have all of those shortcut rules. We didn't know the chain rule or any of these formulas for actually doing derivatives, so we couldn't actually answer a lot of those application questions. So in chapter 4 now, we're going to use all these shortcut rules, use the product rule and the chain rule and all of those other formulas to find derivatives, and then apply them to various situations. So one situation you might want to apply a derivative to is to find the maximum or minimum value of a function, and that's what 4.1, 4.2, and 4.3 are about, and then that shows up in a couple other places in chapter 4. So let's try this. This is all a review of stuff from chapter 2. So give these a shot. I'll warn you actually that for warm-up number 1, some of these may have more than one answer. That's my hint. So fill in the blanks with as many of these statements, A, B, C, D, E, or F, to make the statements over here true. And then use this graph of f of x to draw a very rough sketch of f prime and of the second derivative, which is the derivative of f prime. It doesn't have to be pretty, so just some kind of thing that shows where the derivative is positive and negative and increasing and decreasing. Just to review what this stuff is all about, because that's what this section 4.1 is going to be all about, but in a lot more depth. So let's try it now, and the answers will appear in 3, 2, 1. For number 1 here, part A, this part A, not this part A. Hey, they're both part A for this one. Anyways, if f prime of x is greater than 0, that means the function is increasing. That's that. If f prime of x is less than 0, that means the function f of x is decreasing. Now for C and D, this is where it gets a little confusing. Hey, part C, the answer is also C, and for part D, the answer is also D. That was a little bit of an accident, but it worked out. Oh well. So anyways, if f double prime of x is greater than 0, that's the derivative of the derivative. So the same principle applies with A and B. If the derivative of a function is positive, then that original function is increasing. It's just that this time it's the derivative of f prime is f double prime. So the derivative of this function is positive, is what this is saying. And when that is true, that means the function f prime is increasing. And same argument for why this is D. And also, we talked about in chapter 2 why having an increasing derivative makes your function concave up, and why having a decreasing derivative makes your function concave down. So that's why E and F goes with that. You might want to review section 2.5 is what is all about concavity and second derivatives. So if you're not sure what C, D, E, and F have to do with each other, you might want to review the video for that section. And for number 2, what I'm doing is first looking at the values of x where f of x is changing from increasing to decreasing, where it looks like the derivative is 0 because the tangent line has a slope of 0. And that looks like that happens at about that value of x, which looks like -2. I don't know if you can see that much resolution, and at about x equals 2. So that's where f prime of x is 0 because the slope is 0 at the original function at those points. And then when x is less than -2, like over here on the left here, you've got positive rates of change, so the derivative should then be positive out here. And in between here, there's negative rates of change, and it looks like it's actually at its most steepest negative rate of change at x equals 0. So that gives you a negative value here, and they're all negative here until it gradually starts flattening out until it has a slope of 0 here. That makes f prime of 2 0, and then starts having positive slopes again after that, and that makes f prime positive out here. Okay. And for f double prime, it looks like we have something with negative slopes, which happens here, until you get to 0 slopes at x equals 0. There the slope is 0, so f double prime should be 0. And here there's positive slopes, so that makes f double prime positive at these values of x. And I should point out that there's other possibilities for the way this could be drawn, depending on how you're interpreting the shape of this. So some people might actually get an answer for f prime that doesn't look quite like this. Maybe you thought it was like flattening out a little bit over here. You might have had something that looks like that. Or maybe you even thought it was less steep over here. It's a little bit hard to tell. Maybe it doesn't actually flatten out. Maybe it's just like this. You wouldn't be able to tell the difference between a function that has a derivative like this purple one or like the blue one. They're going to look pretty similar. But then it will come out really differently with the second derivative, like it would come out looking something like that maybe. And so if you have an answer like this, that's okay. As long as the second derivative is positive and negative in the right places, that's okay. So let's see what's next. Okay, so this problem is a pretty mean problem. Oh shoot, it doesn't quite fit. So we're graphing this function here by finding where the function is increasing, where it's decreasing, and where it's concave up, and where it's concave down, using the derivatives to see where the derivatives are positive or negative, and where the second derivatives are positive and negative for the concavity part. And a question like this, first of all, you notice like it's only asking you to graph a function. You could easily go to Desmos.com or use your graphing calculator to just plug it in and graph it and then draw a picture of it here. That's not what this question is about. It's a question about using information from derivatives. So if this question was going to be on a test, what I would do is say no graphing calculators allowed for the test. All you're allowed to do with calculators are basic arithmetic for this kind of thing. So I would probably give you one on a test where you wouldn't have to use a calculator for any arithmetic. So anyways, let's give this a shot. Let's see how we can do it. First, to see where it's increasing and decreasing, we need to know when the first derivative is positive and negative. So let's go through how to find out what values of x make f prime of x positive and what make it negative. That will answer this question about increasing and decreasing. So to do that, we're going to need to find the derivative of this, like so. So that's the first derivative. And to know where this is positive or negative without graphing it with a calculator, which is not allowed here. Maybe we can check our answers at the end, but we got to do it by hand first. To know where this is positive or negative, it would help to know where it's 0. So I'm going to set this equal to 0 and then solve that equation here. I'll start by just factoring out the 3 because these are all divisible by 3. And let's then factor x squared minus 6x minus 16, like so. If you need two numbers that multiply to make negative 16 and add up to negative 6, the negative 8 and 2 will do it, so that works. So this is going to be equal to 0 at these values of x that make these two factors 0. So x minus 8 will be 0 exactly when x equals positive 8. or when x equals -2. And you have to have this whole thing factored completely in order to do that. If you plug these into the thing, it makes 3 times a factor of 0 times something else, anything times 0 is 0. So these are the values of x that make f prime 0. So once you know that, we can figure out where it's positive or negative. So let's just think a little bit about what a graph of f prime of x looks like, this kind of function. And this is going to be true not just for parabolas like this. F prime in this case is a quadratic function, but it's also true for any continuous function, this idea I'm about to tell you about. So if I was going to make a graph of f prime, let's say that this is the x-axis here. And if you plug in x equals -8, which is somewhere over here, the result's going to be 0, so it has that point on it. And then, oh, sorry, that's let's make that be -2. Whoops. And +8 is going to be somewhere over here. And what the graph of this has to look like, if we're thinking, where is f prime of x positive if I'm graphing this? It's going to cross the x-axis at these places, so it might look something like this. Or it might look something like this. Well, we know it's not that in this case because this is a quadratic function. But if it wasn't a quadratic function, maybe it would do something like that. Or it might do something like this. Those are all possibilities of what this could do. And what I want to point out about all of these is it never changes from being positive to being negative at any values of x other than where it's equal to 0. The only way it can cross the x-axis is by crossing through y equals 0 first. So we're not allowed to do anything like have something that goes up like this, and then there's a gap like this, and then it goes like that. That's changing from positive to negative at this value of x, but that only happens if your function is discontinuous. So as long as you have a continuous function, it's either going to be all positive or all negative in each of these 3 intervals. So we make this this thing I call a sign chart here. SIGN, not to be confused with a sign chart. So this is a sign chart because what we're going to do is we're going to figure out what it is f of x positive here, or is it going to be negative? Here, is it going to be positive, or is it going to be negative here? Here, is it going to be positive or negative? And what we can do to find that is just plug in one value of x. So let's say we want to plug in x is -3 here. Cutting myself off there because I made a mistake and I caught it in time, so I'm fixing it. So we're plugging in -3, and we want to know is f prime of x positive or negative there. So f prime of -3, if we do all of this arithmetic, will become 27, which is a positive number, which means that that f prime of x is not negative ever for any values of x less than -2. So if you plug in -2.1 or -5 or anything into f prime, it's guaranteed to always be positive because there's no way it could cross the x-axis again, because we found out the only places where it crosses the x-axis right here. So that's that. Then we can plug in into f prime a number like 0 and a number like 9 here, and see whether we get a positive result or a negative result to tell you about all of the other points in the interval as well. So f prime of 0, I like to plug in 0 because it's really easy to do arithmetic that way, came out to be -48. So that means f prime of -1 is negative, f prime of 7 is negative, but then at 8 it might switch here. We're going to get f prime of 9 becomes a positive number, and that means that's going to be positive. Okay, so that means if we were going to make a rough sketch of f prime of x here, it's going to look something like that. That's a really ugly parabola that I'm like drawing there on the x-axis. That's what this sign chart tells us. So anyways, this is a sign chart for f prime. So we could use that to draw a graph of it now by finding some of we see where it's increasing and decreasing at least. So we could also say that f is increasing on the interval from -infinity to -2, and on the interval from 8 to infinity. And we can say that f is decreasing on the interval from -2 to 8. And you could use that to draw a decent graph of this function. But let's also figure out where it's concave up and concave down by getting the second derivative, because we want to see where the second derivative is positive or negative. So to find the second derivative, I just took the first derivative and did the derivative of that. That's what second derivative means, and got 6x minus 18. And I'm going to do the same thing with a sign chart too, just to practice how it works, even though at this point you could probably graph this. So we want to figure out where is this function equal to 0, and once we know where it's equal to 0, that's where it changes between being positive and negative, so we can plug in a few test points. So if you set this equal to 0, you can factor out a 6 and write x minus 3, and you can see that this is only equal to 0 and x is 3. So if we're going to make a sign chart, it's going to, that's the place where it can change between being positive and negative. So for the sign chart, here's the x-axis at x equals 3, f double prime is 0. Let's plug in a couple other numbers that are easy to do arithmetic with, like one like 0 and one like 4 maybe, and find f double prime of 0 and f double prime of 4, and f double prime of 0 is negative 18, and f double prime of 4 is 6. So that means f double prime is negative for all values of x less than 3, and positive for all values of x greater than 3, because it can't cross at any other points. All right, so this tells us where f is increasing and decreasing, and where it's concave up and concave down. Let's just write that here. So we've got that, the intervals where it's concave up and concave down. Now to actually make a graph of it, we need more than this. We need some actual y coordinates at these important points. So to get those y coordinates, so we can actually get a nice looking graph, not just a graph that has the right shape more or less, but that actually has the right coordinates on it, we're going to need to find some function values here. So let's find f of -2. Let's find f of 8, and f of 3 is another important point, and then we can graph all of these xy points. To calculate these, I ended up using a calculator. Even though I said you shouldn't use a calculator for graphing these, sometimes you have to do it for arithmetic. And like I said, if this shows up on a test, I will give you numbers smaller than this so that you don't have to do all of this arithmetic with a number like 8. I did it with -2 was okay, and I got 104. And I didn't feel like doing all of the big numbers with x equals 8 in my head. So that gives you xy points, and then we can draw some kind of graph of it. So let's make some axes and try to scale them so this stuff will fit. So we've got something like this, and so let's look at what we have about it. Where is it increasing and where is it decreasing, so we can draw it in here. It's increasing until we get to -2, and that's going to happen when y is 104 here. So I'm going to try to draw that part of that. So it's going to have this point about right here on it. And that's going to be where it's increasing, and then after that point it starts decreasing until we get to where x equals 8, and then it will start increasing again. And x equals 8 is where it was -396, just about -400 right there. And let's also plot this point, -2, 100, or sorry, 3, -146, I mean. Which is about there. Okay, so then let's try to graph it. We have something that is increasing until it gets to this point, and then it's going to decrease until it gets to this point. And all the way to the left of 3, it has to be concave down. So I'm going to try to draw something that is concave down. Definitely do this with a pencil because it's tricky to get it looking right. So something kind of like this. Let me start over. I'm going to try to go from this point over to here, and then it should have that point there, and then be concave down afterwards. Okay, so that part looks okay. Increasing, then decreasing, and concave down all the way. And then it needs to be decreasing until we get to this point, and then start increasing again. And you get something like that. And so now this is a pretty decent, accurate graph of this function. We're describing the shape of it, these points where it's at its like highest point and lowest points here, although it's not really the highest point and lowest points for the whole thing because it keeps coming down here and it keeps going up that way probably. At this point, let's just check the results by looking at a graph. Oh, look, I already did it, so I could check my work as I was going. I hope that doesn't count as cheating, but I'll get it on a similar scale so that we can see it. Yeah, so that looks about right. It's got its minimum at about 8, -400, a little maximum value here. But speaking of maximums and minimums, let's define what we mean by that. So a local minimum at a value of x equals p it's an input value that makes the function always less than other f of x values for x near p. So for example, if we had actually let's look at the GeoGebra version. With this thing, if we're talking about 8, plugging in x equals 8 gives you that result of -396 here. And if we zoom in closer and closer here, you can see if you take any other values of x that are not 8, but are near 8, like 8.5 or 7.5 or anything like that, they all give you y coordinates that are slightly higher than f of 8. So that makes f of 8 a local minimum. Sometimes they'll say f of 8 is a local minimum, or sometimes they'll just say 8 is a local minimum of the function, but it means the same thing. And likewise, you have a local maximum at a value of x equals p if f of p is greater or equal to f of x. And that happened over here at x equals -2. F of -2 was 104. That's slightly greater than all of the other f of x values near it. So, and we say local because it's only greater, like f of -2, for example, it's only greater than f of x values for numbers near here, like in between -1 and -3. Because if you zoom out more, there's f of x values that are greater if we go over here. Like here's a f of x value that is 300, which is bigger than 104. So that's what we mean by local, just in that locality of it, right around there, in the neighborhood of p. So let's check if you understand this definition by trying example 2. This is one you should definitely do. Here's a function that has this domain from -2 to 6. So that includes -2, so f of -2 is defined, but f of 6 is undefined. It just has a vertical asymptote at 6. So find the local mins and the local maxes of this function. And I'm going to pause it, and you should pause it because the answers will appear in 3, 2, 1. Here are those solutions. The local mins are at -2 and 2, and also at x equals 5 here, and there's only one local maximum at x equal 0, so maybe I shouldn't make that plural. So why is it these numbers? Let's go over that. So if you plug in -2 here, the y coordinate that you get is that y coordinate. That y coordinate is a little bit less than all of these other y coordinates that you could get by plugging in values of x that are a little bit greater than -2, like -1.9. And you can't even plug in -2.1 because that's not in the domain, so it doesn't matter. As long as f of -2 is less than or equal to function values that actually exist near -2, that works. And the same thing happens with 2. You can see f of 2 is that height, but f of 1.9 or f of 2.1, those y coordinates are all bigger than f of 2, so that makes 2 a local minimum. And then x equals 5 is a little bit weird. So looking at this one, if you plug in 5, you get that, but then if you plug in anything like 4.9, you'll get something a little bit bigger. And also if you plug in something like 5.1, you'll get something over here. And so f of 5.1 is much greater than f of 5, but it's still greater. So that makes 5 a local minimum. And you can also see that x equals 0 is a local maximum. That's happening here where the derivative is equal to 0 at that point. But you might think some of these other points might be local maximums as well, such as, like, what about 3? Well, actually, 3, if you plug in f of 3, you're going to get this point down here, and you might be thinking this point is a local maximum here, but it's not actually, because if you plug in something a little bit bigger than 3, really close to 3, you're going to get, if you plug in 3.1, you're going to get something that's bigger than f of 3. So that means f of 3 is not a maximum because there's function values very near it that are greater than f of 3. And also, what about like 3.0001 or something? If you have this open circle here, you might want to pick a point very close to it. So f of 3.001 is not a bad idea, but can you pick something where f is a little bit bigger than f of 3.001? You actually can. If you pick f of 3.000001, that's going to be very slightly bigger than f of 3.001 because you're getting a little bit higher if you go closer to the left. And this isn't a maximum either because you can get still just slightly bigger by plugging in something slightly closer to 3. So there's no maximum anywhere near x equals 3. And also near 6, it just keeps getting bigger. So you could do f of 5.9 is going to be pretty big up here, but then you can get a little bit bigger by doing f of 5.99, which in turn is less than f of 5.999, etc. You can always keep going up higher towards infinity here as you plug in x values that are getting closer and closer to 6. So there's no maximum there either. And by the way, I'm using the word mins and maxes, but if we're going to do a little side note here about some spelling. So there's a lot of Latin-based words in English, as you know, like bacteria. And you might know the singular of bacteria, if you're just talking about one of them, is called a bacterium. And there's a lot of words like that, like criteria is the plural of criterium. If you have more than one stratum, they are strata. And also, minimum and maximum are like that too. They're from Latin. So the official plural word for minima, for minimum is minima, and for maximum is maxima, just like with bacteria. Now, that's getting kind of pedantic. And it turns out also stadium is a Latin-based noun, and the proper way to pluralize stadium is to say stadia. So like we're going to have the Olympics in Los Angeles in a few years, so they are going to need many stadia for it. But if you say that, you're going to sound like a pedantic asshole. But if you want to sound like a pedantic asshole, you can say minima and maxima all the time. Or I shouldn't make fun of people that say that because that is really the correct way to say it. Anyways, back over here. So yeah, these are minima and only one maximum. So here's an important fact, that if a point is either a local min or a local max, then one of these things must be true about that value of x. Either it's a critical point, which means that the derivative of the function there is 0, or is undefined, or it's an endpoint of the domain. So let's just look at this last example. The critical points here, the points where f prime is 0 or undefined, in this one, those are at x equals 0 and x equals 2 and x equals 3 and x equals 5. Those are the places where the derivative is either 0 or undefined. And I say 3 and 5 because if it's discontinuous, it's not differentiable. Every differentiable function is continuous, so it's not that the derivative at 3 or 5 is undefined there. Also at x equals 2, the derivative is undefined. X equals 0 is the only one here where it's actually 0. And then there's also the endpoints of the domain. So in this case, the only endpoint of the domain was at x equals -2. X equals 6 isn't really an endpoint, well, because it's not in the domain itself, so it's f of 6 is undefined anyway, so it doesn't matter. So all of the things we have are all of the minimums or maximums we have are either one of these critical points, or they are the endpoint in the domain, which is -2. So this is an important thing to keep in mind because we use this to figure out where local mins and local maxes are. So here's a couple theorems. Are these actually theorems in the book? Or are they just rules? It doesn't really matter. They are facts that we can actually use to more specifically tell if something is a minimum or a maximum. So I'm going to leave these blank. Each of these blanks is either minimum or a maximum, but I'm hoping that you can fill in the blank yourself is a good way to practice figuring it out. If not, I'll fill it in just a moment. But let's read this. if x equals p is a critical point, meaning the derivative f prime of p is either 0 or undefined, then as x increases, meaning as you go from left to right on the graph, if f prime of x changes from negative to positive, then p is a local. Let's think. What does that look like when f prime changes from negative to positive? On the graph of x, it would look like f is decreasing, and then as you go to the right, it starts increasing again. And that's what's happening here. You have f prime of x negative here, so this is like a graph of f, but f prime would be less than 0 on this side, and then f prime would be greater than 0 on the right side. And when that happens, you go from decreasing to increasing. That makes p a local minimum. And vice versa, if you go from having f prime being greater than 0, because your original function is increasing, to then you go to where p here, in this example, f prime of p is undefined here if this is a sharp corner, but then after that it turns that sharp corner and you have f prime is less than 0 after that. So from positive to negative slopes, that means you must have a local maximum. Okay, so this first derivative test always works for pretty much any time you have a critical point. You can use this if it's possible to conclude that you have a minimum or a maximum. This will tell you. But there are some times where you don't have to do that, and I usually prefer to use what's called the second derivative test, which doesn't apply to as many situations as this one. So for example, if you have a sharp corner here on your graph of f of x, then the second derivative test doesn't work. But the second derivative test works for most functions. Let's look at what this says. If f prime of p is 0, so that's not only a critical point, but it means f prime is defined, and it's flat there, and it's like smoothly flat, kind of like this first example here. And f double prime is greater than 0. Let's think, what does that mean? That means it's concave, or the original function f is concave up. Then let's see, what does it have to look like if you have a point here where the derivative is 0, but the graph is concave up? It must look like that. That's really the only way to draw a concave up function where the derivative at that point is 0. That makes p a local minimum. And this is actually a drawing of that too. But then this is saying if the second part here says if f prime of p is 0 and f double prime is less than 0, that means f is concave down, and we have a slope of 0 at that point p. The only way to draw a concave down graph is here. I mean, like if you try to draw something that's concave down here, you're gonna fail. It doesn't quite work. It has to be like this is the only way to draw a concave down graph. That makes p a local maximum. One more thing I need to mention before this next bigger example we're going to do is a point where f of x changes concavity is called an inflection point, meaning where it goes from concave up to concave down or vice versa. It's a term we use sometimes. We have one back up here where we did this one. When f double prime with this example changed from being negative to being positive here, and the graph of f then had what was concave down and then became concave up after it, that makes this an inflection point. And sometimes I'll say 3 is an inflection point, or I might just say the point 3 negative 146 is the inflection point. So that's an inflection point. Let's do another example here. So here's example 3. This is one you should try at this point, hopefully. It's pretty similar to example 1, but we want to use, you could do this either using the first derivative test or using the second derivative test. So you'll need to find g prime, figure out where g prime is greater than 0, where it's less than 0, and also maybe try to use the second derivative test by finding g double prime. So I'm actually going to do this here. If you want to try it on your own, you can pause it and then fast forward a little bit to see if your answers are matching along with mine, or if you feel a little intimidated or whatever, you can just watch, but I recommend trying it. So here's the way I would do it. We need to find the critical points to see where g prime of x is either 0 or undefined. So of course we need g prime of x, so let's do that. So using the product rule here, because this function is a product of these two functions, first the original x times the derivative of e to the negative x, which itself requires a chain rule. We need to multiply by the derivative of negative x, which is -1 on the outside there. And then we can do the derivative of x is 1 times the original e to the negative x there. And that's that. And we want to know where is this equal to 0. So at critical points, this would be 0. And by the way, it's either 0 or undefined, but this is actually defined for all values of x. There's nothing here that would make you divide by 0 or anything else that's undefined. So yeah, the original function was actually differentiable everywhere. So this is never undefined. So we don't need to worry about making that undefined, but it could be equal to 0. So I'm going to set this equal to 0. And then it looks like we could factor out an e to the negative x. That's always a helpful thing if you're trying to make something 0, is to factor it and then set the factors to 0. So what will be left is that -1 times x, just negative x, and then plus 1 over here. And so if either of these factors are ever equal to 0, that will make the whole thing be 0 and give you a critical point. So e to the negative x actually is equal to 0 never. Let's just look at a graph of e to the negative x first to make sure of that. Here's a nice graph of y equals e to the negative x. It's like a regular exponential function, just turned around from left to right. So you can see what happens here is it gets very close to 0. It gets very close to 0. This is approximately 0 here, but not quite. So yeah, it's actually e to any power, it doesn't matter what, is never 0. So that doesn't give you any critical points, but this one here will give you critical points when x equals 1. We'll make that be 0. So that's a critical point. That's a place where it might change from positive to negative. So let's look at the second derivative now. So to get the second derivative of this, I'm just going to use this version right here and this version of g prime and use the product rule with it, or you could use this other one here, it doesn't matter. So here's the derivative of this using the product rule. First, the original e to the negative x times the derivative here of that negative x, plus the derivative of e to the negative x here using the chain rule times the original second factor. And this one, we should factor this one out as well. And we probably want to know where it's equal to 0. And so, yeah, let's factor out that. Well, actually, we could just factor out a negative e to the negative x, because both of these have a -1 factor. That will make it a little easier. And then we'll have 1 times that here. plus x minus 1 times negative x plus 1 here. So that will be 1 minus x plus 1, also known as 2 minus x. Okay, so that's the second derivative, and if we want to find inflection points are going to be where this changes from positive to negative. So just like with first derivatives, we probably want to know where it's equal to 0. So let's actually make a sign chart here to figure out the concavity of this function. And to make the sign chart, we need to first find where is g prime equal to 0. And again, negative e to the negative x is never 0, so we don't need to worry about that. But this will be equal to 0 if x is 2. That will make this thing 0. So 2 is like our critical point sort of thing, but we're not going to call it that because that's only for first derivatives. And if we want to graph g double prime here to figure out where it's positive and where it's negative, first I would just plug in a number less than 2, like 1, and find g double prime of 1. Let's do that right here. So g double prime of 1 is going to be negative e to the negative 1 times 2 minus 1, which is 1. That's going to be a negative number times 1 is less than 0. So this is g prime is negative here for all values of x less than 2. And it's also, let's see what happens if you plug in something like 3 here. G double prime of 3 is going to be negative e to the negative 3, which is a very small negative number, times 2 minus 3 is negative 1. So that's actually going to be positive. So that tells us that 2 is an inflection point. X equals 2 is an inflection point. It goes from being concave down to concave up. And actually, let's just look what we figured out about our critical point before. We just found out that since g, the second derivative here, let's look at the second derivative test. The second derivative is negative, so the function is concave down. So we're talking about something like this kind of graph. And that means that x equals 1 is actually a maximum, a local maximum. And we also just figured out that 2 is a critical point, sorry, an inflection point. So that's actually enough to graph it at this point, except we should actually get some y coordinates of the original function so we know what it looks like. And let's see what that looks like. So we need to get let's get g of 0 because that's one of the endpoints. And g of the critical point, we're going to need that. And let's plug in the inflection point as well into this thing, and we'll get some estimates here. So that's what I got here. G of 0 is 0, G of 1 is 0.36, and G of 2 is 0.27. And that gives you basically enough to graph it. So let's graph it here. So I got those 3 points. And let's see, I know it's going to be increasing up to this point. And then after that point, it's going to be decreasing, and it will continue being concave down until we get to x equals 2. So there's something kind of concave down there. And then at x equals 2 is where it's going to have its steepest negative slope and then start flattening out again. So it's going to do something like this. Whoops. Like that. It needs to be decreasing as you go forward because Oh, we didn't actually prove that? Well, you can tell here if you look at this g prime of x, if x is greater than 1, anything greater than 1 is automatically going to make this whole thing negative. So it's going to be decreasing and concave up all the way out there. And we didn't actually prove that the limit is 0, like maybe it's actually approaching 0.1 or something like that, but the limit is 0. So it looks something like that. And I haven't quite answered the question because there's one thing I missed. I said we have a local maximum and we have an inflection point, but have I found all of the mins and maxes? Not quite, because I haven't checked the endpoint of the domain, and you can just tell from the graph that that makes it a local minimum. So there is a complete graph of that and the complete answer with the local min at x equals 0, local max at 1, and inflection point at x equals 2. Let's look at another one where we can sort of use the first derivative test here. You should try this one on your own, mostly because it's really quick and you won't have to waste too much time being stuck with it if you don't know how to do it. So you might just get it wrong, and that's okay, and it will just take a minute. And so do this one now. Make a rough sketch of f of x given the graph of f prime. Notice that you're doing this backwards than the usual way. So I'll tell you right now, the answer is not going to be something like a line that goes through x equals 3, the point 3, 0. That would be if you were drawing the derivative of this, but you're going backwards. This is the derivative. You need to draw the original function. It is a little tricky, but give it a shot, and the answers will appear in 3, 2, 1. So here is one possible answer for that. The important thing is that you should have a local maximum here where f prime changes from being positive to being negative. And then wherever f prime is negative here below the x-axis, then f of x should be decreasing. And then when f prime is equal to 0 at x equals 7, that's where this should be flat, and then from there it should start increasing again. And this point, x equals 3, it's supposed to be a inflection point, because that's the point where f prime of x is flat, so the derivative should be 0. So f double prime will be 0 there, and yeah, my graph isn't perfect because it's hard to draw smooth curves on this thing, but it should be an inflection point. Here's some practice problems to try now at the end. So this problem number 2 is pretty similar to the one we just did, that last example. And problem number 1 is similar to the other ones where you're finding the derivative and setting it equal to 0. So yeah, find this derivative, set it equal to 0, and use that to figure out where f prime is positive and negative. And then for practice problem number 2, same idea as that last example. So do these, and the answers will appear in 3, 2, 1. Here are some answers to these. So problem number 1 gives you x equals z. So first of all, here's a derivative. I used the product rule. You can pause it and check that if you got something else. Then setting that equal to 0, I first factored it. I factored out an x squared from it and factored out an e to the x. And that leaves you with x squared e to the x times x plus 3. Then there are 3 factors here that might be 0. X squared is 0 when x is 0. E to the x is never 0 for any value of x. And x plus 3 is 0 when x is negative 3. So those are the possible places where f prime could change sign from negative to positive or positive to negative. And so to set up the sign chart, I want to plot, I want to plug in something like -4 into it. to see if f prime is positive or negative there. I got a negative number. If you do f prime of -1, you get a positive number. F prime of +1 is positive as well. So that's that sign chart. And it's a good idea to check your answer to something like this by just making a quick graph of it with some software. I'm going to just make a quick graph of f of x. It looks about like that. So here you can see -3 is it is flat there, so it's a critical point, and it's the original function is decreasing, then it's increasing again here, and that's what this said it should be doing. If f prime is negative and changes to positive, then that means f is changing from decreasing to increasing, and that's what we see here. And then it flattens out again right here, but it doesn't actually turn around and start decreasing. It just flattens out and then keeps going up again after that. So the tangent line is horizontal here, but that doesn't make it actually a minimum or maximum. So the only actual minimum or maximum that this one has is at -3, where it changes from decreasing to increasing. So that's that problem. And here's my g of x based on the graph of g prime. So again, I looked at where g prime is equal to 0 here. That means the original function that I'm trying to draw should be horizontal. So again, backwards from the normal way we do problems like this. And where g prime is negative, I want to draw something decreasing. So I drew something here that goes from being decreasing when g prime is negative to increasing again when g prime becomes positive at these values of x. And then the point where g should be the steepest positive slope is right here, where g prime is at its maximum positive value. So that's actually going to be an inflection point. And from that point, g prime starts decreasing, so that means g should be concave down out here. And it looks like it's not only concave down, but it's approaching being horizontal the further to the right we go, because g prime gets closer and closer to being 0 the further to the right we go. So anyways, that's this section. It's a pretty long one. There's a lot of stuff in the section. So thanks for bearing with it. We're gonna do some practice of this in class, and have a good day or night or whatever, and I'll see you on Tuesday.